Hello and welcome. In this video, we're going to talk about a very popular machine learning algorithm that's known as the naive Bayes algorithm. It's very popular because it relies on one of the most fundamental concepts of probabilities, that's Bayes' theorem. So in a way, while going through this video, you will get to know about this algorithm, plus you'll get a refresher on some of the key concepts of probability. We will start our discussion by considering a problem. So let's say we are trying to help an internet service provider. And at most of the places, the internet services are provided on a subscription basis. So we have a couple of fields which talk about consumption. And we've captured this in the form of a yes or no. So did the customer spend usual or more time using internet? So this is some kind of a time measure which is indicating the consumption of internet. Then the second piece is interruption. So did the customer face any service interruption? If there was an interruption, most likely would have received a complaint or request to solve that problem. And finally, this is the column which we want to predict. We want to predict the renewal based on the consumption and interruption history. We want to predict if a customer is likely to review for the next month or not. Here is the data. So this is just a sample of the overall data, let's say, and we've captured all these variables in the form of binaries, which means these are yes, no. But naive Bayes also can be applied for variables which are continuous in nature or numerical in nature. And we'll talk about that too. But let's just first get started with this example. So assume that we have a lot of data, but we're just looking at the first 10 records. We have the consumption. Was this the usual or more consumption? If yes, then it's a Y, otherwise it's a no. And interruption, if there was no interruption, then it is an N here. If there was an interruption, then it's a yes here. And finally, the target column, again in the form of whether the customer has renewed or not renewed. Notice this is the historical data. So you are going to make a prediction given these inputs, but in order to be able to come up with a model, you need to feed the model the actual data, which means you need to tell the model about the historical target labels. Let's say we consider the first case. Here's historical data related to a consumer who had the consumption in place and no interruption. And obviously this consumer had renewed. So this is history. Similarly, this is the case where the consumption was in place. There was an interruption, and probably because of that, the customer did not renew. So all of this is history. All we have to do here is that when we get a new input, let's say in the form of a consumption being a no, which means the consumption was not usual and interruption was not there, can you predict whether a customer would renew or not? So using the intelligence derived from the historical data, we have to make a prediction for the future. In other words, we can say we are interested in predicting a probability of a yes for renewal, given that consumption was not in place and there was no interruption in the services. So let's first consider this probability equation. This is what we are solving. And just as a refresher on probabilities, let's understand the concept of conditional probabilities. By the way, we've done a couple of detailed videos on conditional probabilities, which happen to be quite popular on the internet. In case you've not watched those, you might want to refer to them. Those videos involve complete theory and solved problems. But if you're comfortable with the basics, we can continue. So conditional probability of an event A given B is written as probability of A intersection B divided by the probability of B. This can further be written as probability of B given A multiplied by the probability of A divided by the probability of B. Now, this is known as the Bayes theorem. Now, the only other piece that you want to consider over and above the conditional probabilities in order to solve such problems is the concept of independence of events. So two events are said to be independent when the occurrence or non-occurrence of one does not affect the other. So probability of A given B, if A and B were independent, would be just the same as probability of A. Similarly, probability of B given A would be just the same as probability of B if A and B are independent, which means the occurrence or non-occurrence of B or A does not affect the other. So using this information on the independence of events, if we focus on this expression, just this piece here right now, you can see the denominator is common. So we can ignore that. Probability of B is there in the division at both the places. We can say probability of A intersection B is equal to probability of B given A multiplied by probability of A. But with this equation, we know that B given A is nothing but probability of B. Using these two, we can rewrite this expression as probability of A intersection B is equal to probability of A multiplied by the probability of B, which is from here we got it. Now coming back to our question was whether a customer would renew or not, provided we know that the consumption was not usual and there was no interruption. We can write this in short like this. So we've just taken the initials and the underscore, that's it, just to simplify the way we write it. Now, remember the formula for conditional probability? So for the time being, just treat these two, consumption no and interruption no, as one event. And just try to fit the formula for conditional probabilities. You'll get something like this. Take your time to follow this. Probability of A given B, so we are calling it as one event. A given B is nothing but B given A multiplied by the probability of A, which is this, divided by the probability of B. And we are saying this consumption no and interruption no is right now being treated as one event. We've just applied the formula for conditional probability. The only difference is here we are looking at just one event as the given event, whereas in this case we are looking at two, but we've just written it in the same way. Now we're going to consider the numerator and denominator pieces separately to be able to get this answer. So let's concentrate on the numerator only for the time being. And this is the numerator in that expression. Now, why this is called naive Bayes? Bayes theorem is understandable. Why is this called naive? It's called naive because it assumes that the variables explaining an outcome would be treated as independent, which means it says there is no connection between the consumption and interruption. These are totally unrelated features. Why is that naive? Because in business context, when you work on certain variables while solving a problem, they tend to have some connection or the other. That might not be very strong, but we can also not say that's totally independent to begin with. So for example, if there was an interruption, could that lead to the drop in consumption? That's possible. Theoretically, we understand that's possible. But naive Bayes says we would assume these to be two independent occurrences. Consumption has no connection with interruption. And if that is the case, then you can break this portion of this expression like this. So if you see, this is the concept of independence. In a way, this is representing the portion which is common between the interruption and consumption. We are saying drop in consumption, which means consumption is not usual given the renewal happens, and there is no interruption given the renewal happens. So we've just broken this into two pieces, and then we have the probability of renewal. Now let's look at the table, the data, the original data that we started with, and we'll have to get these answers from here. Now, the easiest one is this piece. Can we get to know the probability of renewal being a yes? That's very simple. We just have to focus on the renewal column, and we have to count the number of yeses. So let's say we have 1, 2, 3, 4, 5, and 6 yeses. Out of how many rows? 10 rows. So we can write this is going to be 6 by 10. Now, if you look at these two pieces here, both of them only consider the event of renewal being the yes. So do we need to look at the overall data? No. From a conditional probability logic perspective, we just need to filter this data for the renewal being yes, which means we only need to consider these rows which are captured in these boxes. The event of renewal being no is not important while solving for this and this. Let's filter the data only for all the yes cases for renewal. And now try to answer this question. What is the probability of consumption being not the usual consumption? If you see, out of 1, 2, 3, 4, 5, 6, 6 cases, there's only one scenario. So 1 by 6 is the probability for this. And what about interruption being a no, given renewal was a yes? So interruption being a no, we have 5 occurrences out of 6. So we can say that's 5 by 6. Now, if we put all these values here, we've solved the numerator. Numerator comes out to 5083. We can do the calculation. Once again, coming back to this piece, this portion is sorted, but we are yet to solve this piece. Now, how do we solve for this, right? So this says we are considering consumption not being usual and interruption not being there in service. Let's see. Now, this is interesting about Bayes theorem. There's a very easy way to write this expression. If you notice, this piece here is nothing but the numerator, the same as the numerator. Plus, what are we adding? See, the only other possibility with these two cases is that your renewal did not happen. So if you put these two together, that will complete that event. So we've already considered this piece in the numerator, and this piece here, if you look at it, is just considering the possibility of renewal not happening. So these two taken together would complete this out. Now we've already solved for this. Pretty similar would be the approach to solve this piece. And then we'll know the denominator as well. So let's consider the second part of the denominator. This talked about the renewal not happening as the given condition. And this time we are talking about the probability of renewal not happening. So if you look at the overall data, out of 10 times, how many times the renewal did not happen? can count this 1, 2, 3, and 4. So this is going to be 4 by 10. This is also known as the prior probability. This is how you'll find it in some of the books. Now, the next piece is everywhere here, we are only considering those cases where the renewal has not happened. So let's filter the data for those choices. 1, 2, 3, and 4. Let's consider such records where the renewal has not happened. And then within those records, look for the consumption not being usual and interruption not happening. So it means we can filter the data to such cases only. And now if we look for this, out of the renewal not happening cases, what is the proportion of cases where the consumption was not usual? You will find this 3 times out of 4. So this is going to be 3 by 4. Out of the cases where the renewal did not happen, what proportion of cases were there where the interruption was not there? You would write it as 1 by 4. Now, all these portions of the expression are known to us. Coming back to the original problem, we've got this value as the numerator already, which was 0.083. And we've just computed this value here, which is 0.075. And let's put these values here, and this is the output that you get. The final probability is 0.053 or approximately 5.3% chance. So there is a 5.3% chance that a customer would renew the subscription provided the consumption last month was not usual and there was no interruption in the service. This is how we solve our Bayes theorem problem. Now you see, this of course gets a lot more complex when you have a large data, but this was just to give you an intuition so that you're able to connect to it. And obviously for large complex data sets, you would not be doing this manually. You will take help from the libraries like scikit-learn and apply the appropriate algorithm. There are many variants of naive Bayes. To begin with, the problem that we were looking at, assume that our data comes from a format which has only binary outcomes, yes or no in both the cases. This specific variant is known as the Bernoulli naive Bayes because you have either a 0 or 1 kind of a possibility, only 2 possible outcomes. But as you can imagine in real world, the data could be very different. For example, if this column interruption starts capturing the number of times the service was interrupted. For example, if it starts reporting a frequency of interruptions, let's say the service in first case got interrupted 3 times. In the second case, it got interrupted 10 times. So these are counts that we are looking at, right? If we have such a scenario, if our data contains such variables, all variables like this, or maybe mix of these variables along with other variables, a better choice would be a multinomial naive Bayes. All these are available in the form of existing libraries in Python, so you would not have to figure out much on that. And what if our data varies a little further? For example, we begin to capture some of the features as continuous variables. So in this case, let's say we were talking about the consumption that a given user has for each month. And let's say we are capturing it in minutes. Now, if you see, this is capturing the duration and it is more of a continuous variable. So in such cases, how do we solve this problem? This falls under the category of Gaussian Naive Bayes. So if you're dealing with continuous features, we may want to satisfy the assumptions relative to normal distribution and then look into the possibility of applying the Gaussian Naive Bayes. So let's reduce our focus only to the consumption and renewal status like this. And now what we have to do is we have to segregate the consumption with respect to renewal. So we have to separate the values of consumption when the renewal status was yes versus when the renewal status was no, like this. So these are the original 10 records. 6 records belong to renewal yes, and 4 records belong to renewal no. Notice we are working on a very small sample of the overall data. Obviously, you would not fit a distribution to 8 or 10 observations normally. You can imagine we have a lot more data, but we are working on a small subsection of the overall data, just to convey the point. Now, if this feature follows the normal distribution, we should be able to compute its mean and standard deviation, mu1 and sigma 1. Similarly, if this feature follows normal distribution, we should be able to calculate its mean and standard deviation, mu2 and sigma 2. And to represent visually, let's assume that we take the consumption column on the x-axis. And we are assuming 2 distributions. On the left, we have the distribution for consumption when we've considered the renewal status to be no. On the right, we have the distribution for consumption when we have considered the renewal status to be yes. These may not be looking identical. These could be different means and standard deviations. But just for demonstration purpose, we've taken similar looking curves. It is not mandatory. Now, there is a point where these 2 normal distributions intersect. We would typically call it a cutoff point. So we can say that if we get a new record for which the consumption value is greater than the cutoff to the right of this blue line, that is more likely to be a renewal yes status. Whereas if for a new record or a consumer, we get to know that the value of consumption is less than the cutoff, which means it is to the left of this blue line, it is more likely to be non-renewing in the subsequent cycle. So that is how we deal with continuous features. In real world, we are most likely to encounter a mix of features. And in such cases, we can use appropriate naive Bayes algorithm. Let's talk about the assumptions relative to naive Bayes. So naive Bayes is pretty relaxed in terms of assumptions. First is, it is called naive. That's how the name comes, because it assumes that the features are independent. That's one of the basic assumptions in case of naive Bayes. Apart from that, naive Bayes is not sensitive to outliers, does not really assume any specific distribution, except for the case when you're dealing with Gaussian naive Bayes. So if you're dealing with Gaussian naive Bayes, then all the assumptions of normality for the continuous variables would play a role here. But also remember, naive Bayes is only a classifier. Naive Bayes would not solve value prediction problems like linear regression. It can compete with a logistic regression in doing classifications. All right, so that concludes our discussion on the naive Bayes algorithm. Hope you had something new to learn.